Alright kids, I know I said the last video was the last video, but it's not. I changed my mind. I wanted to go ahead and make videos that go with my last two lessons. I may or may not force you to watch them, but at least now they're here for those who need them, right? So, this one is over radians and general angles. So the first thing we're going to talk about are angles in standard position. So imagine an x and a y axis. And just like a clock, our angles will be anchored at the very center, and they will always have the initial side fixed on the x-axis, on the positive x-axis, right here. It will always start right there. We will then rotate our angle counterclockwise. Always goes counterclockwise, and then wherever it ends, this one I drew ending over here, but you could draw it ending anywhere, right? Anywhere. Wherever it ends, that's your terminal side. And if you didn't already know, a full rotation of a circle would be 360 degrees. So half of that's 180 degrees. That's 90 degrees. You learned all that in geometry, I hope. So here's some examples. Draw each of these angles in standard position. All right, you will have one of these on the test, I know for sure. So we're always going to put our vertex on the origin. We're always going to put our initial side. It doesn't matter how long you draw it because you're putting an arrow on the end. It extends out forever. It's a ray. And we want to draw 240 degrees. All right, so we know 90's here, 180's here, and then we need 60 more to get to 240. It's 90 to get to the bottom, so we know it's about 60 more would be at about right there. And notice I just estimated. That's okay for you to estimate as long as you're in the right quadrant and as long as you write 240 degrees on it. If you write how much it's supposed to be, I will take your word for it. If you don't write it and it's supposed to be 240, I'm going to have to get out my protractor, and you better hope you actually drew it at 240 degrees. So one more time, you must have an initial side with an arrow. You must have a terminal side with an arrow. You must draw the rotation and indicate the direction it rotated, and you must write how much it is. Got it? Good. So now we're going to draw a negative 50-degree angle. We have to start at the origin. We have to start on the positive x-axis. If a positive angle is counterclockwise, then a negative angle will be clockwise. So we're going to go this way. And negative 50, that's just a little bit more than 45. 45 is halfway between here. So I'm going to go just a little bit more than 45. Once again, I eyeballed it, I guessed at it, because I'm going to write negative 50 degrees here. And as long as we're in the right quadrant, we're close. If you write it on there, you're good. And one thing I see a lot is people will write this, they'll draw this, but they won't draw this. It's not an angle if you only draw one part of it. You have to actually draw both parts of it. You can't just let the printed x-axis count. That doesn't count. So, how would you draw something that was 500 degrees? We would start at the origin, initial side on the x-axis, and then we would draw a full rotation around like a snail kinda, because that's 360 degrees. And then if I needed to go all the way to 500, well, let's see, what is 500 minus 360? That's going to be 140 degrees more. So I went around 360 already, and then I need to go 140 more. I know this is where 180 hits, so it's going to be over here. So you'll draw the spiral, implying the direction and writing 500 degrees on it. So that what differentiates this from a 140 degree angle, 4D degree, sorry, is that we drew the spiral. This makes it 500. If you were to draw that, it would be 140 degrees. Sure, your initial and terminal sides are in the same place, And so you could call it a 140-degree angle, but you have to draw the stuff in here to determine which one it actually is. And there's a big vocabulary word for that, coterminal. Coterminal means they share a terminal side, right? They terminate in the same place. So if I were to ask you, find one positive and one negative angle coterminal with a 45-degree angle. Well, a 45-degree angle starts on the positive x-axis and ends there, right? That would be a 45-degree angle. If I wanted to say a positive one, well, think about what we just did. If we started and went and spiraled around, how many degrees would that spiral be? Well, we would just have to take 360 and add the 45 to it, because the circle part's 360 and then the extra is 45, and so we get 405 degrees. So 405 degrees would be one positive angle, coterminal with 45 degrees. We could also do a negative. We could start here and go back, because remember, negative angles go clockwise. So if we went back, we would be going 360 minus 45. Gives us 315, and since we were going back, make sure you make it negative 315 degrees. So basically the trick is to add or subtract multiples of 360. Multiples of 360, because I could go around 360, and then 360 more, and then 360 more, and then add 45, right? That would be the same angle. You can add many, many, many multiples of 360, so you're going to add and subtract multiples of 360. And I usually just go with one, add one for one round or subtract one round, but you could do as many as you wanted, really. All right, so next up, radian measure. A radian is the measure of an angle in standard position whose terminal side intersects an arc of length r. Here, if I have my radius, this is the radius of the circle, right? If I measured that with a tape measure that was floppy, and then I laid that along the edge, it would be about right there, right? So there's the radius, this is the radius, this is also the length of the radius. The angle that creates right here, theta, is 1 radian. 1 radian is an angle in standard position whose terminal side intercepts an arc of length r. If we create the arc that has the same length as this, then the angle that we get is 1 radian. Now think about what you know about a circle. Circumference is 2 pi r, right? And so that's saying 2 pi's times the radius, or radius times 2 pi. And think about that. You know pi is 3.14, so 2 of those would be about 6.28. We could fit this in our circle 6.28 times. 1, 2, 3.14, 4, 5, 6, there's 0.28. Okay? Trust me, you'll learn a lot more about it next year in pre-cal, but we just wanted to introduce it to you. I think you might have already seen this before, but just in case you haven't, that's what a radian is. So there are 2 pi radians in a circle. So just like we can measure temperature in Fahrenheit or Celsius, we can measure our angles in degrees or radians. And so to convert, here's how you do your conversions. Your circle has 360 degrees in it. We all know this. We also just learned that it has 2 pi radians. So 360 equals 2 pi, or 1 degree. If I divided both sides by 360, keep pi as a symbol, but 2 over 360 reduces to 1 over 180. So to get degrees, we're going to multiply our degrees times pi over 180, and that will give you your radians. Okay? multiply your degrees times pi over 180. Because see, your degree here will cancel out with your degree here, and you will have a pi in your answer, and radians most usually, not always, but usually have the pi in their answer. If you wanted to convert the other way, we would just take the radians, multiply by the reciprocal, which is 180 over pi. So see, this is degrees, this is radians, so your radians cancel out and you end up with degrees. So first example, let's convert 75 degrees to radians. Well, you can look at a circle and you can figure out where it is, but we know we need to just take our 75, multiply it by pi over 180. 75 degrees times pi over 180 gives us, you just leave pi as a symbol, and 75 over 180 reduces to 5/12. So we have 5 pi over 180, and that's radians. So now try a different one. Convert negative 5 pi over 4 to degrees. It's customary when we use radians, we just don't put any symbol, any units is what I'm trying to say. So you'll see it, and if it doesn't have any units, you should know it's radians if we're talking about angles. So we're going to convert negative 5 pi over 4. That means we have to take negative 5 pi over 4. We need to multiply it by 180 over pi. I know that a lot of people get mixed up. They're like, what do I multiply by? Pi over 180 or 180 over pi? But really, just think, I got to get this pi away from there because there's no pi's in my degrees, so I know I have to multiply it by the one with the pi in the bottom, right, so that they'll just cancel out. I don't even need to multiply pi. And then I just need to do negative 5 times 180 and divided by 4, and then I get a negative 225 degrees. Oh, correction. How many of y'all caught this? It's not 5 pi over 180. It's 5 pi over 12. That's supposed to be a 12. So yeah, special prize for you if you caught that, right? There you go, 5 pi over 12. Okay, now we're going to divide our circle up. We've done some of this already. I just want to go through the whole circle. We know this is 0 degrees. And if you go all the way around it, it's 360 degrees. So we know halfway is 180 degrees. Then if you want to know up here, well, we should all know this is 90 degrees, but you could just cut the 180 in half, right? And if I wanted halfway between 180 and 360, that's 270 degrees right here. Then we can divide it even further. So here, if I divide it up even further like this, well, then that's not what I wanted to do. Okay, sorry. Get the pen out. That's 45 degrees. And then from between 90 and 180, halfway between is going to be 135 degrees. And halfway between 180 and 270 is going to be 225 degrees. Did it again. There. Halfway between 270 and 360, or 270 plus 45 more, would be 315 degrees. And then 45 more gives us 360. Now, we'll go in our 30-degree increments, or our thirds. So maybe this will help. I used teal lines to show dividing the top half into thirds and the bottom half into thirds. So, this would be 60 degrees right here, right? Because a third of 180 is 60. And then each of these pieces, each of these is 60 degrees. So 60 plus 60 is 120, plus 60 is 180, plus 60 is 240, plus 60 is 300, plus 60 gives us 360 degrees. Now let's do sixths. So now if you just look at the teal lines, I've divided the top into 6 and the bottom into 6. So that's 30 degrees, plus 30 more is 60, plus 30 more is 90, plus 30 more is 120, plus 30 more is going to be 150 degrees. 30 more is 180, 30 more is going to be 210 degrees. 30 more is 240, and then 270, and then 300, and then this will be 330 degrees. So we're just dividing it up into equal increments, and those are the ones that we're going to use the most in our trigonometry, because those are our special triangles. We get 45, 45, 90s, and 30, 60, 90s. But now I want us to convert all of this to radians. Okay, so let's start here, 0 radians. And if we go all the way around a whole circle, we have 2 pi radians, which means half of the circle is pi, right? So if I'm going to divide this up, first thing I'm going to do is go, okay, well, up here, that's half of pi. Pi over 2. Pi over 2 radians. So that's half. That's 2 halves, which is 1. Down here we have 3 halves. 3 pi over 2 radians. And then all the way around is 4 halves. Each of these quarters of the circle is a half of a pi. And so we have 4 halves, which is 2 pi all the way around. All right, and then we can do the next easy ones. 45 degrees is a fourth, pi over 4, because half of a half is a fourth. So there's 1/4, 2/4, 3/4, 3 pi over 4. 4/4 is 1, 5/4, 5 pi over 4. 6/4 is 3 halves, 7/4, 7 pi over 4, and then 8/4, which is 2 pi. All right, and then we can move on to the 30, 60, 90s. So I've got kind of a mess going on here. I'm going to try to clean it up just so we can understand a little bit. Use a different color. Let's see. Let's go with green. And let's go with a thicker marker. Sorry, I'm talking through this. All right, so each of these is a sixth, right? So that means that this is going to be pi over 6. And this is going to be 2 pi over 6, which is 1 pi over 3. Pi over 3. Oh, that's a bad color. Pi over 3. Pi over 6. Right? Then this green one right up here, still pi over 2, because it would be 1/6, 2/6, 3/6 is pi over 2. 3/6 is a half. This is the 4th 6. 4/6 reduces to 2/3, 2 pi over 3. This is the 5th 6, so it's 5 pi over 6. This is your 6th 6, which is pi. This is your 7th 6, 7 pi over 6. Here's the 8th 6, 8 pi over 6, which is going to reduce to 4 pi over 3. The 9th 6 is 3 pi over 2. The 10th 6, 10 over 6 is 5 pi over 3. The 11th 6, 11 pi over 6. And then the 12th 6, which is back to being 2 pi. Ugh. But really, it's just dividing the circle up into even fractions all the way around. We've got fourths and we've got sixths. So if you can just think of it that way, you can set this up. And you'll use this so many times in pre-cal, you'll be sick of it, I promise. All right, this is a long video, I'm sorry, I know. But we have one more section to do, arc length and sector area. Okay, so for arc length, we're just going to set up a proportion, just like you did in geometry. Our arc length is a part of the circumference. And that's going to be proportional to the angle that goes with that arc over the angle in a whole circle. So if our arc length is S, and our circumference is 2 pi r, the central angle is theta, and then the angle of a circle, we now know in radians, is 2 pi. So very, very important that we say this has to be in radians. Has to be. This won't work if we don't use radians. You could do a proportion with degrees as long as you keep theta in degrees as well. But if I simplify this, if I cross multiply, the 2 pi's can just cancel out. See? And if you're in degrees, you can't do that. And so the formula for arc length in radians, S equals r theta. It's very simple and easy as long as you keep theta in radians. Now for sector area, it's going to be the same type of proportion. We're going to take the sector area out of the area of the whole circle. Will also be proportional to our angle theta over the angle of the circle. So if we let the sector area be A, the area of a circle is pi r squared, the central angle is theta, and the angle of the circle in radians once again is 2 pi. This time only pi can cancel out, and when we cross multiply, we get A equals r squared theta, it's a square, over 2. And so that's a very simple formula you can use as long as you're using radians. So I have an example. A softball field needs a new fence along the outfield edge. That's this edge right here, for those of you who don't know. And new grass. And look at it, it's grass on the whole thing, right? They can wear their own base paths, but we're just going to give them new grass on the whole thing. How much should be ordered? So for the fence, we want the arc length. We're going to give this a 90-degree angle right there. So if I use the formula, S equals r theta. My radius, my r, if this were drawn as a whole circle, would be 180. And then my theta, this is a right angle. But I'm not going to use 90. If I multiply 180 times 90, I'm going to get 16,000 feet of fence. And common sense should tell you that this curve is not 16,000 feet long. We need to do 90 degrees, which is pi over 2 in radians. And then you can punch that into your calculator, since when you order fence, you're not going to say, I want 90 pi feet of fence. You're going to say, I want 283 feet of fence, which sounds a lot more logical. All right, now for the grass. We know the area is r squared theta over 2. So we need 180 squared times pi over 2, and then all divided by 2. And when you punch that in, you should get 25,447 square feet of grass. If you used 90 instead of pi over 2, you'd have in the millions. And we know that's not millions of square feet. So use some common sense when you do this. But if you know the formulas, it's really easy. All right, and since this video is long enough, I'm going to stop and be done. And y'all have a good whatever rest of your day. And I'll see you later.